Good morning all. So this is my first video through this YouTube. Earlier we had two classes where we discussed about the syllabus and then we discussed about why we have to learn the subject and in what perspective that we have to learn the subject, and not but in particular the subject, all the subjects pertaining to engineering, because it's a professional course. And in particular, why we have to learn this subject, what we will learn, what will be the outcome of this subject after learning this course at the end of the semester. After learning this course, what are the different outcomes? So we have to satisfy all the outcomes. So there is a purpose for learning this subject. And then in yesterday's class, in the second half, we discussed about the different standards, that is absolute standards, primary standards, secondary standards, and working standards. So today's class we'll see about the different system performance. There are different parameters for a measuring device. A measuring system itself is a standalone device, so it has its own performance. So broadly we classify such a system in two ways. That is, it is having two characteristics, that is static characteristics and dynamic characteristics. So static characteristics are pertaining to certain parameters or instruments, measuring instruments, when the quantity under measurement, when the quantity under measurement is either constant or varying slowly with time. So if an instrument measures a quantity which is either constant or varying slowly with time, then the parameters will be described as static characteristics. Static characteristics. They do not change with respect to time, or they are very slowly changing with time. For example, if we have a thermometer, so thermometer, we know the purpose of thermometer is to measure the temperature. So we know that temperature is not a constant, but variation in temperature is very slow. That is one thing. So we can include the characteristics of the measuring instruments under static characteristics. Likewise, 230 volt, the AC voltage, the single phase AC voltage 230 volt that we have uh, in our supply, single phase supply. So 230 volt is there will be variations, but that variations will be plus or minus within plus or minus 6% of the 230 volt. So that again is slow. It is, we can consider it as a constant. It is supposed to be a constant, but certain variation is allowed. So that within that variation, it is constant. So that is why we use a voltmeter there. So that characteristics also comes under static characteristics. So what all parameters will be coming under dynamic characteristics? See, dynamic characteristics means there are certain parameters, there are certain quantities which have to be measured, but they are not at all constant, but they are varying very fast with respect to time. So they are not only variable thing, but they are varying very fast with respect to time. There are many quantities which are varying very in a very fast manner with respect to time. So in such way, there are in such conditions there are another characteristics that is called dynamic characteristics, and they are described with differential equations. I hope you have learned about differential equations in the second semester. Okay, so these are the things we have to understand in the preliminary system performance, and then we will go to the two things, that is static characteristics first. So these are the different characteristics, different parameters that will be coming under static parameters. That is, one is accuracy, sensitivity, reproducibility, drift, static error, and dead zone. So the first three characteristics are required. They are necessary characteristics. That is, accuracy, sensitivity, and reproducibility are necessary things. But drift, static error, and dead zone are not at all necessary. They are not at all required, and they are totally undesirable. So 4, 5, 6 are undesirable, whereas 1, 2, 3 are desirable. So first we'll see about static error, and I'll be moving very slowly in the first few lectures. So we'll see what is happening in static error. So we know that there are errors in measurements. There are errors in measurement. So any measurement device will have its own errors, or the human errors can creep in. So many things will contribute to errors. We'll see that in detail later. So Okay, so first of all, before going to the error, let me take two things. That is, first one is what is true value. Anyway, we are measuring a quantity. It can be a temperature, it can be voltage, it can be current, anything. Any quantity that we are measuring will have a true value. We are trying to attain, or we are trying to catch up, or we are trying to measure that true value. So what is true value? So we know that while we conduct experiments, you may have conducted experiments in electronics workshop, like the VI characteristics of diode, or verification of Ohm's law in +2, that is in physics lab, verification of Ohm's law. Let us take the verification of Ohm's law itself. It's a very simple experiment. It's a simple circuit where we have two meters, that is voltmeter and ammeter. Taking the ratio of voltmeter and ammeter, then we'll get the resistance value. But we never take a single value and stop the experiment. We take numerous values. We take numerous chances. That is, one trial, second reading, third reading, fourth reading, maybe 5 or 6 or 7 readings we'll take, and then we'll calculate for each of the reading. We'll calculate V by I, and we'll get the value for R. And at the end, we say that we take the average value of all the R values, and we tell that this is my R value. What is the purpose of taking so many readings for an experiment, so many takes for an experiment, so many trials for an experiment? The purpose is that actually, if it is an ideal one, then it is required. Then its requirement is only to take one value. So why it is necessary to take so many readings, so many trials in an experiment? The thing is that they can change. The first reading may change from the second reading. The second reading may change from the third reading. Likewise, ideally there should not be any change, but there can be deviations. So that is why we take so many trials, so that we have to verify that this is some set of reading. Suppose if we take some 7 readings, 5 readings may be consistent, remaining 2 may not be consistent. So that 2 readings we may discard. So the 5 readings which are consistent, or which are coming as a group, we take it and we take the average. So the highly inconsistent readings we discard. That is another advantage of taking so many trials. So why the true value? So how do you take true value? Let us conduct an experiment. We take infinite number of readings, and finally we see that when we take infinite number of readings, finally we see that the average deviation due to varying contribution factors, the deviation occurs due to varying contributing factors, average deviation between the readings tends to 0. Such an ideal situation is impossible to realize in practice. You just imagine, taking infinite number of readings itself is not possible. Infinity is not at all a number. We cannot measure infinity. So nobody knows which is infinity. So sky is a limit. So infinite number of reading itself is not at all possible. Suppose we take infinite number of readings, and if the average deviation, that is, if we have that is, if we have equal number of negative deviations and positive deviations, if we sum it up and take the average, then of course the numerator will be 0. That is the meaning of average deviation tends to 0. So in that case, the value is called, the measured value, that the result we get out of the experiment is called the true value. So this is an ideal way of defining true value. So this is the actual true value. And then what is actually, so how do we get the true value? The true value is nothing but there are some exemplar methods defined by experts. So the outcome of such experiments, exemplar methods, outcome of such experiments devised by experts is called true value. For example, in yesterday's class, I told that potentiometer is the ideal way of getting the unknown voltage. So potentiometer, the reading of the potentiometer, the outcome of the potentiometer experiment will be a true value. So the potentiometer that we know is that it is having null deflection method. It will be following null deflection method. So more or less it is giving correct value of the potential drop or the voltage. So in such a way, that can be taken as true value. So this true value can be compared or can be used to calibrate a voltmeter. So any exemplar method devised by expert can tell you a true value, or so by definition, that is infinite number of chances, the average deviation, and then if the average deviation tends to 0, then that is called a true value. That is the definition. But any exemplar method that an expert devises, the result of that such exemplar method experiment can be called as a true value. Then what is the actual value? Then next one is the actual value. Actual value is nothing but what we conduct experiment. We in lab also we conduct experiment. So that the outcome, I told that we'll take several trials. We may, if suppose if we take 7 trials, out of that 2 may be highly inconsistent reading, we may discard that. So the consistent grouping may be 5 readings. So that 5 readings we take, and if we take the average. Why we take the average? The average deviations, in some sense, some deviations will be cancelled. That is why we take the average of that 5 readings, and that average of that 5 readings will get the average, sorry, the actual value. So true value is there, then the actual value is also there. So we strive the measurement, while taking while conducting the experiment or while measuring a quantity, we strive to achieve the true value. But how long we can achieve, how close is the actual value to the true value, that is another thing. So the best measured value, that is the closer the actual value to the true value, will reduce the error. So we are actually talking about error. So that is where it's called, since it's a static characteristic, this parameter is called static error. That is the closeness of the actually measured value to the true value. So already I have designed what is true value, it will reduce the error. So we will see what is error. So we cannot avoid errors to an extent. We can minimize it, but we cannot avoid it, because practically that is always there. So that is the measured quantity. So this is the measured quantity of the actual value we are talking about, minus the true value, will get the error. So delta A is nothing but the error. So delta A is also called represented as epsilon naught, or it is sometimes referred as eta naught, or epsilon naught. I'll take it as epsilon naught. So this is nothing but the absolute static error of the quantity under measurement. And many times this does not have any meaning. That is, suppose if my static error is for a measurement of a current, if the static error, that is delta A, if I am getting it as plus or minus 2 amps, does it make any sense? That's another thing. That is, suppose you have several marks with you in your class. For physics you have such marks, so many marks. One student got 30 marks, one student got 45 marks, one student got 60 marks. So 30, 45 and 60. If I do not mention out of how many marks you got 30, 45 and 60, then it is absolutely meaningless. 45 it is out of 50, then it's a good mark. 45 out of 100, okay, it's a pass mark. 45 out of 200, it's absolute, it's a fail mark. So if you don't have a proper reference, then the quantity you are specifying is absolutely meaningless. That is, plus or minus 2 amps doesn't make any sense if you don't mention the proper things. That is, if you are measuring, if you are measuring an amps in 1000 amps, in the range of 1000 amps you are measuring currents, and then plus or minus 2 amps is not at all a proper error. It's not a proper error, it's negligibly small error. 1000 minus 2 amps means 998 amps, plus 2 means 1002 amps. So 1000 plus 2 amps doesn't make, it's more or less 1000. 1000 minus 2 amps is also more or less 1000. But if the same error is coming under measure, if the same error is coming for the measurement of a 10 amps, then that is intolerable. 10 minus 2 is 8 amps, so a very huge deviation. 10 plus 2, 12 amps, that is again another huge deviation. So simply specifying static error doesn't make any sense. So you have to tell it in another way, that is called relative error. So what is a relative error? Relative error is nothing but epsilon r, that is the ratio of absolute error to true value. So we know what the representation for absolute error, that is delta A, and the true value is AT. So absolute error can be represented as epsilon naught by true value. So this much you just see and watch repeatedly and understand. Remaining things we'll see in the next class. Thank you.